Hello everyone, I'm Nolan Welberger. Thanks for joining me on this adventure. We're looking at dynamics on graphs, and I'm wanting to apply what we've learned, the mutation game, the numbers game, ADE graphs, to the standard model of physics, in particular the numerology, the connections with certain patterns of numbers that was discovered in the 1960s. And I want to show you, first of all, a non-standard way of looking at this. So this will, I think, be interesting to physicists. But also, we're going to setting ourselves up for being able to explain this story, this aspect of the standard model, without resort to the representation theory of SU3, which is the usual method that's done, which requires all kinds of prior understanding, rather sophisticated knowledge, representations and Lie groups, etc. So we're going to sort of finesse that and have another way of, a much simpler way of looking at this. And basically all what's really involved is this mutation game and numbers game and associated geometry and algebra. Okay, so to motivate the discussion, around the 1960s, the physicists sort of discovered that the large array of particles that they had discovered in the accelerators and cloud chambers and such could be organized in certain fashions, at least some of them could be, by looking at certain quantum numbers and sort of arranging these particles in certain configurations. And prominent amongst them is something called the baryon multiplet, or sometimes baryon octet, which gives rise to the eightfold way. And this was initiated by Gell-Mann and Neyman around early 1960s. So there are 8 particles here. Prominently up here is the neutron and the proton, which are the standard sort of basic building blocks of matter, along with the electron and photon perhaps. And then there's some other particles which are much more amorphous. They only last for a split second, like a millisecond or less in a cloud chamber or particle accelerator. So they decay very quickly, but still they are there. And there's 3 sigma particles. There's I guess a lambda particle and 2 psi particles. And it turns out that they form this sort of eightfold pattern with 6 around the outside and 2 in the middle when we organize them in terms of charge, Q, and another quantum number called strangeness, S, which is having values 0, -1, and -2. So one of the ideas that I'm going to advocate here is that we should actually replace strangeness with another quantum number. I'll explain that later. It's called hypercharge. And that happens to have values y equals 1, y equals 0, and y equals -1. Okay? And then that gives us an opportunity of reconfiguring what this octet really looks like in this sort of configuration space with charge in one direction and hypercharge in another. So I'm going to reposition that usual picture of the baryon multiplet or octet by introducing the Q1 to be the charge axis and Q2 to be the hypercharge axis. And then when we plot our 8 particles, we have a neutron here, the proton is then here, the sigma particles, the lambda particle, and these 2 psi particles arranged now in this sort of elongated hexagon, which maybe looks a little bit familiar if you remember the root system for the simple graph A2. Okay, so here are the roots. There are 6 roots of A2, and they're given by these vectors, and these are exactly the vectors or positions that we see here on the defining this hexagon outside. So that's a first indication that maybe there's some connection between this elementary particle story and this A2 graph. So to set the stage, let me just give you a very, very quick overview of some of the basic ideas of the standard model, which is the current theory that explains or tries to explain the zoo of elementary particles that we currently have. Okay, so there are 4 important forces in physics. There's gravity, that's the most sort of obvious one. It's not directly relevant for the standard model, at least not currently, although people are working very hard to try to incorporate it into the standard model, but that's a huge challenge. But in the standard model itself, there are 3 forces that are at work. There's electromagnetism, which involves electrons and photons. And then there's the weak force, which is much harder to see. It's responsible for decay of particles, and there are some particular particles called W and Z bosons, which sort of create this weak force. And then there's the strong force, which binds the nucleons together, that is the neutrons and protons that form the nucleons of atoms. And this is where the quarks come in, and also the particles that sort of mediate this force, called gluons. Okay, so the Standard Model is concerned with these three forces, and these days these are described in terms of what's called gauge groups. So there's the U1 for electromagnetism, and SU2 for a weak force, and SU3 for the strong force. And we'll talk about these things later. So this is a very interesting and elaborate story. I don't really know that much about it, but we're going to be concentrating on trying to understand the particles in the context of these three forces. Okay, so there's a whole range of particles, and most of them are just lasting a very brief amount of time, but still physicists want to try to understand nature, and so part of that story is to try to explain these particles. And physicists have categorized these, so there's certain terms that really you need to have some basic familiarity with, and this is my attempt at sort of roughly sketching what these various classifications are. So this is not meant to be entirely accurate. Probably I'm leaving some things out, and maybe I've put some things in the wrong places, but roughly the idea is something like this. A first subdivision of the particles is into fermions and bosons. So this column is the fermions, this column is the bosons. And that has to do with distinguishing the type of spin that these elementary particles have. Now this is a little bit somehow analogous to a top spinning around, but it's something different. It's a different kind of spin. Okay, that's a little bit hard to visualize. But in any case, some particles have integer value of spin. So spin is a number, like one, spin of 1, spin of 2, spin of 3, etc. But you can also have half integer spin, like spin of a half or spin of minus a half. And the fermions are the ones that have half integer spin, and the bosons are the ones that have integer spin. Now, this is a very important distinction because it turns out that these particles obey sort of different rules called statistics. So these ones obey what are called Fermi-Dirac statistics, and these ones Bose-Einstein statistics. And the crucial difference is that the fermions obey the Pauli exclusion principle, which prohibits two particles of the same type from occupying the same state, from being together, at the same time. Okay, now there's another subdivision corresponding to the rows here that roughly corresponds to whether the particles feel the strong force or don't feel the strong force. Okay, so the hadrons are the particles that feel the strong force, and the other ones, I don't know if there's actually a name for them, but they're the ones that don't feel the strong force. Okay, so the fermions, which do feel the strong force, are called baryons, and the fermions which don't feel the strong force are called leptons. So that's a basic subdivision. And in some sense, these are sort of the main classes of particles that actually contribute to matter, to the stuff around us. Now, in this baryon box, we see, first of all, prominently the quarks. Although technically speaking, probably the hadron means a composite particle, so maybe quarks are actually officially excluded, but okay. So quarks are sort of really elementary kind of particles that come in 6 different flavors: up, down, strange, charm, top, and bottom. Okay, we'll talk about that later. And also they come in 3 colors: blue, red, and green. So there's the world of quarks, whatever they are. And then there are other families of baryons, and it turns out that they form sort of patterns, just like the one that I've showed you, that baryon multiplet or baryon octet. So there was a picture of that baryon octet, okay? And then there's another picture of baryon decuplet like that has a bunch of particles that form a triangular pattern like this. The leptons are also fermions, so they also obey the Pauli exclusion principle, and the most notable one there is the electron. And then there are other versions, sort of more massive versions of the electron called the muon and the tau particles. And then there's also neutrinos, which are sort of weird things that don't seem to pay any attention to anything, and they just zip through everything. Okay, on the boson side, the things with integer spin, the things that don't obey the Pauli exclusion principle, we have the mesons. So these are the ones that are basically somehow associated with quarks. And so examples of them are gluons, and okay, there's also multiplets that are associated with them. So here's a meson nonet, it's called, which we'll talk about shortly. And then mesons which don't feel the strong force, well, there's the photon, and then the W and Z bosons, which are involved with the weak force. And then there's this sort of remarkable, relatively new particle called the Higgs particle, which was discovered only less than 10 years ago. And okay, so very roughly, this is sort of a classification. There are, of course, lots of particles in these boxes, typically, especially in these ones here. But this is a rough classification. So fermions and bosons, important. And then there's the baryons and the leptons. They're types of fermions. And then there's also mesons, which are bosons, but they share the property of the baryons that they're basically built from quarks, roughly. So they're involved in the strong interaction. And then these other bosons are involved with other interactions, either electromagnetism or the weak force. Okay, very rough overview. Okay, and the other important ingredient that we need to talk about are quantum numbers. So these are numbers that one associates to elementary particles that are conserved in particle interactions. So if there's a collision, then you total up the total of this whatever quantum number you're interested in before and after, and those two numbers should agree. So the most famous such quantum number is charge, denoted by Q. And then there's something called isospin, which is denoted by I, and then there's sort of a Z coordinate of the isospin called I sub Z. And I should say that there's some sensitivity here in terms of what kind of particle interactions we're talking about, okay? So some of these quantum numbers are invariant under all interactions, and some of them only for strong or perhaps only for weak interactions. So, you know, the situation is a little bit more complicated, but I'm just giving you a very brief overview. And this is roughly, you know, around the 1960s that the picture was like this. Since then, there are more quantum numbers that have been discovered. So baryon number is an important number. That's just the number of baryons. So the ones in that box that I showed you, okay? So if you count the number of baryons at the beginning of some interaction and the number of baryons at the end, they should match up. And similarly with the leptons. So, you know, the actual particles can change their nature, but the total number of leptons to begin with and the total number of leptons at the end should also match. In fact, there's further subdivisions here, but we'll just leave it at that. And then there's this thing called strangeness, which I believe was introduced by Murray Gell-Mann going back into the 50s. And they noticed that certain particles that we thought were associated with the strong force also somehow were affected by the weak force in a perhaps strange way. And so this was called strangeness, and this quantum number is a sort of a measure of the extent to which particles do that. And then there's something called hypercharge. And maybe one way of thinking about hypercharge is it's the sum of the strangeness and the baryon number. And this is quite important for us because this Y is the same one that I introduced when I was talking about the baryon multiplet as an alternative scale. Instead of using strangeness, we were using the hypercharge. And then there's a famous relation due to Gell-Mann and Nishijima that relates the charge, the Z component of the isospin, and the hypercharge. It's Q equals I sub Z plus 1/2 Y. So these things are all, you know, connected. And let me state again, this is only very roughly. Actually, later on, there were more quantum numbers associated with other quarks, in fact, and this equation has to be modified, etc. But very roughly, this is the idea. And this is a really important one for us because we're going to be changing our point of view. Instead of strangeness, we're going to be focusing on hypercharge. Okay, so the next little grouping that we want to talk about is called the meson nonet, nonet for 9. And it looks a lot like the baryon octet that I was showing you before, except that there are 3 mesons in that central position. And the quantum numbers that we're interested in are the same ones as previously. The charge here, -1, 0, 1, and the strangeness 1, 0, -1. Now remember I said that I want to convert things to hypercharge, so I have to also tell you what the hypercharge is. And to get the hypercharge, we take the strangeness and we add the baryon number. Baryon number. Okay, so what are these things? These are mesons. So baryons and mesons are both hadrons. They're both particles that feel the strong force, but these ones are bosons. The other ones were fermions. So the bosons are not baryons. So these guys all have baryon numbers of 0, which means that their hypercharge actually equals their strangeness. So y equals 1, y equals 0, and y equals -1. So actually make no difference in this case here. Okay, so this is the usual picture that one sees in texts and papers of the mesons, at least some of the mesons. Okay, so here's our straightened view of this meson nonet. Our axis here of charge, which we might call Q1, and here's hypercharge, this y, which is the same as Q2. And I've just plotted the various points now, and we get something very similar looking as we did for the baryon multiplet. K0, K plus, pi minus, pi 0, pi plus, and there's also an eta and eta prime, and a K minus and a K bar 0. Okay, so there's the meson nonet in this sort of straightened form where we don't have 60-degree angles, we've made everything rectangular. There's really good advantages to that, as we'll see later on when we connect with the mutation game and the numbers game and associated geometry. Okay, and now we come to another pattern, this time also of baryons, and this is called the baryon decouplet, because there's 10 particles in this little family or grouping. And there are 4 delta particles, okay, delta minus, delta 0, delta plus, delta double plus, and then some sigma particles, but sigma star minus, sigma star 0, sigma star plus, 2 psi particles, psi star minus, psi star 0, and then another one down here at the bottom, quite a different name, omega minus. This one's actually quite important in this story because Gell-Mann famously predicted the existence of this particle before it actually had been discovered by observing that these particles created this pattern when we plot them in the familiar way with charge along these lines here, charge going -1, 0, 1, and 2, and strangeness 0, -1, -2, -3. So he noticed that this natural pattern had something missing here, and so he said, oh, there should be a particle there, and he was able to predict what kind of characteristics it had, and then the experimentalists were able to go out, and a year or two later, they discovered this particle in their accelerators, and this was a huge confirmation of the essential validity of this 8-fold way and this approach to the classification of elementary particles. So these are all baryons, okay? They're baryons, so when we want to convert the strangeness to hypercharge, remember the hypercharge is strangeness plus baryon number. These are all baryons, so we should add 1. So hypercharge equals 1, hypercharge equals 0, hypercharge equals -1, and hypercharge equals -2. Okay, so when we plot these 10 particles in the same context as before, charge in this direction, hypercharge in this direction. So now the delta particles go from a charge of -1 to a charge of 2, but their y value is 1, not 0 as it was before. And here's the sigma star particles, the psi star particles, and our omega minus down here. So it's quite an attractive view. We get a nice triangle. And notice that it's sort of a uniform triangle in the sense that the multiplicity of the inside here is the same. So it's sort of like flat multiplicities. Okay, so once the physicists had put these families of particles together on nice patterns, two-dimensional patterns corresponding to these quantum numbers, they realized that this suggested to them that there were actually underlying more elementary particles that could be used as building blocks for this zoo of baryons and mesons that they had found. And these new particles became known as quarks, and they are now sort of the central objects in some sense of the Standard Model. And the way this comes about is through this diagram. So here, again, we have charge and hypercharge with the same axes as before. And I've labeled the points where we've already had some particles. So we can superimpose all three diagrams, the baryon octet, the meson nonet, and the baryon decuplet, all on the same diagram. But it would get a little bit confusing. But I've just put some of them here. So there's the neutron there, and the proton. There's K0, K+, those are mesons, and here are a few of the delta particles, delta minus, delta plus plus, and a few others. There's omega minus down there. There's pi minus. Okay, what are the new particles that are suggested? So they realized that there were three other kinds of particles that you couldn't observe directly, but that had sort of an indirect existence because we could build up these other particles in terms of these three, actually, and their antiparticles. So there's actually three new particles, three new quarks, and their antiparticles. So they're called up, down, and strange. And here are where they are on this diagram. Okay, so up is at the point with coordinates 2/3 and 1/3 when we're measuring with respect to charge and hypercharge. Okay, crucially not strange, hypercharge. The down quark is minus 1/3 charge and plus 1/3 hypercharge. And the strange is minus 1/3 charge and minus 2/3 hypercharge. So now they all have antiparticles. And the antiparticles are sort of opposite in pretty well every sense. So the antiparticle of up is down here. So this is a 2/3, a 1/3. So we have to go to minus 2/3, minus 1/3. I guess that would be about right there. Okay, so that's a kind of an antiparticle to up. So this is called up bar. It's the antiparticle, the antiquark to up. Similarly, there's an antiparticle to down. There it is there. So that's D bar. And there's an antiparticle to S. That's, we have to go 1/3, 2/3 up here. So that's S bar. And those three antiparticles also form a kind of a triangle. So let's make dotted lines between them. Okay, so there's sort of two triangles of quarks here. There's up, down, strange, and the antiparticles of those, up bar, down bar, strange bar. And now a miraculous thing happens, that just by looking at the geometry of this diagram, we can sort of decompose these various particles that we previously had thought were sort of elementary. We can now decompose these into these perhaps somewhat ephemeral quarks and antiquarks. So let me show you how that's done. So the neutron, for example, how do you get the neutron? So the neutron is a baryon which has half integral spin, and these quarks all have half integral spin also, as it turns out. So we need three of these quarks or antiquarks to make these baryons. So this baryon here is, let's see, 1 up and 2 downs. So you see that sort of vector. Think of this vector. It's like the vector D. That's the vector U, if you like. Okay. So to get to neutron, we go up and then 2 downs. That's telling us that the neutron is composed of 1 up and 2 downs. How about the proton? Well, of course, there's 3 particles here. So the decomposition here is not actually unique, but it's sort of probably unique if you restrict yourself in some reasonably natural way. So the proton turns out to be 2 ups, so go up, up here, and then a down. So this is up, up, down. So let's just stop here and pause. So this is a remarkable thing that we're postulating the existence of these new particles, which actually are not visible. No one's actually observed a quark or an antiquark directly. They seem to always be bound together with other quarks. They're not appearing in nature by themselves. okay, for various reasons. So they're almost impossible to verify their existence, actually. But so we have a lot of indirect evidence, maybe not entirely conclusive in my mind. I mean, I think one should maintain a bit of skepticism here, but at least mathematically, it's interesting to think of these as sort of constituents of these more elaborate particles. So for example, this delta plus, that's a baryon, so it's also made out of three of these quarks, and not too hard to see that it's got to be three of these ups. Okay, so there's up, up, up. And similar to this omega minus down here, for example, that's going to be 1, 2, 3, three S's. Strange, strange, strange. The pi minus, how are we going to get that one? So we want to cook this. This is a meson. Okay, mesons have integral spin, so we should take two quarks, or two quark / anti-quarks. Okay, so what we can do here, if we want to get to this one, what we could do is we could go have a down and then an up bar. Okay, that's like the up bar vector there. Okay, the negative of the up vector. So there it is there. If we combine that with this one, we get the pi minus. So that's the combination of a down and anti-up. So quarks and anti-quarks can combine to also make particles. So then it's an interesting exercise to say, okay, well, what about all of them? And can we do this sort of consistently in a nice fashion? And I think that's a really important exercise to illustrate what's going on. And that's what I'm going to do in my next video. So I want to carry on with this and show you exactly how we can get the presumed decomposition of all these baryons and mesons that I've shown you today in terms of the three fundamental quarks, up, down, strange, and their antiparticles.